Well, it's the physics video lecture once again. Physics 4B video lecture 16. We're talking about capacitance. We're going to wrap up this chapter and move on into some more circuitry. Actually, we'll begin talking about circuitry. But yeah, let's do a little bit more with capacitance. The capacitor will be our first circuit element, and we have Q equals CV, or Q equals C delta V, depending on how you want to write it. And we already have this parallel plate capacitor, so this becomes our capacitor, and I'll introduce the battery here as well. Okay, so we'll have our V, and this would be the positive and the negative side, and then we'll have our capacitor C here, and what happens is, and we'll investigate the time dependence of how it happens, but for now we hook the capacitor up and eventually we get positive Q and negative Q on the respective plates of the capacitor. So what we're going to do next is find capacitors in parallel and series. So capacitors, we'll say in combination, and learn about equivalent capacitances. Okay. So that's our next topic here, and it starts us off in some basic circuit elements. So let's see, we start with capacitors in parallel. So what does that mean? Parallel capacitors. So we'll do the same thing we have right there. We've got our battery. It's enough to know there's plus and minus there. And what we do is we have capacitors mounted like this, and what's peculiar to this setup, this is called wiring it in parallel, is that both capacitors here, this one is C1 and this is C sub 2, they both have the same voltage or potential difference across them. Okay. And what we want to do is find the equivalent capacitance. So we know, because we just did it, that we just wired up two capacitors like this, but suppose they were enclosed, and so we just had these two leads coming out of them, and the question is, what would the capacitance be of this mystery capacitor? That's one way to look at it. So let's quickly apply that definition. Okay. And what we see is the charge is the capacitance times the voltage. So what we have for this set here, let's go ahead and write find equivalent capacitance. And what we have now is Q equals CV for both of these. So we have Q1 equals C1 times V, right? They both have the same voltage. Q2 equals C2 times V. And therefore, Q1 plus Q2 equals C equivalent times V. Okay. So I can put parentheses, right? This is the total charge, equivalent capacitance, voltage, and so almost trivially, we just plug in what we have up here and we see the equivalent capacitance is C1 plus C2. And if you had a whole ladder of these, a whole series of them, we would just add them linearly. So for the equivalent capacitance for capacitors wired in parallel, so parallel, I'll go ahead and start right here. We have C equivalent C1 plus C2 plus, and so on. If you have 3, 4, 5, then you would just add them that way. So that's the first type of wiring, and it's characterized by the fact that they both have the same potential across them. Now, series is the other fundamental way of putting things together. So for the series capacitance, let's go ahead and put our battery here, and we're going to wire two capacitors where you go in one side and out the other, so to speak. Okay. And this again is C1 and this is C2. And we wait a while and they're now charged up. So here the situation's interesting because they no longer have the same voltage across them. If this is V here, there's going to be a voltage V1 and a voltage V2 across them, such that these two voltages, V1 plus V2, equal to V. Okay. So that's the first point to be made. In terms of the charges on the capacitors, we can think of these two outside plates as having plus Q and minus Q on them, which means that in series, the two capacitors are going to actually have to have the same charge. So based on that, we're going to say plus Q, minus Q right here, and plus Q right there. So plus minus, plus minus. And that allows us to now use this definition again here. Namely, we have Q is the same and V is what's different. So we have V is equal to Q over C1, right? V, I have to solve for V here. So V1 is equal to Q over C1, that's an equal sign. V2 is equal to Q over C2. Okay, so now we're going to, let me go ahead and erase this here. Eraser, yeah. So we combine these now, and we can add the two. V1 plus V2 is equal to V on the one hand. On the other hand, it's equal to Q times 1 over C1 plus 1 over C2. Just from these expressions right here. This is the same charge Q on both of them. And now look at our definition. Generally speaking, Q is C equivalent times, well, we're using this one, C equivalent times V. Okay. And so the equivalent capacitance, 1 over the equivalent capacitance is going to be sum of these reciprocals right here. So from this, and note again, Q is equal to C equivalent times V. So C equivalent would be Q divided by V. Okay. So C equivalent Q divided by V, and immediately 1 over C equivalent 1 over C1 plus 1 over C2. So they add as the reciprocals, and you can also keep adding 1 over C3, 1 over C4 with the same logic. So good. What do we have here? Let's go ahead and put them in red. These are our equivalent capacitances or capacitors in parallel, and this is equivalent when you're wired in series. I'm going to assign a couple of these problems. You can kind of treat them like puzzles. There's just a couple basic rules. And what we're going to do for the couple of homework assignment problems that I assign is be given a certain, I'll even draw one of them. We'll be given a little combination. We'll be given a combination of capacitors and just answer every question about them that's possible. So I'll show you what that is. And it's good practice for what's to come, but we don't have to do too much of it, so we'll just do a couple of these. I'm just going to write homework example. I'm pretty sure this is what it's going to look like. Suppose you have, we can put our battery here. Suppose we have a scenario where we have two capacitors here. Okay, so they're in series, C1 and C2, but then we have a third capacitor in parallel here, C3. And this here is our voltage, and eventually these things are all charged up. So what you're going to try to do in a situation like this is find the equivalent capacitance for the whole thing. And once you have that, because you have the voltage here as well, you then have the charges on here, and the charges on each of these. And if you have the charge on any of these, then you also have the voltage drop across them. For example, the voltage across here is just V, but over here you have to note that it's V1 plus V2 is going to be equal to that same V as we just did up here. So find C equivalent, find all voltage drops. We're just using voltage drop and voltage interchangeably. And find the energy stored in each capacitor. So these capacitors are devices for storing charge and storing energy. We talked about the energy storage last time. So those are all just very basic formulas. We'll do a couple of these. It's good practice. And I think I'll leave it at that. Oh, actually, one more brief topic. So I'll just write here, finally, capacitors and dielectrics. And this is just going to add, no big deal, capacitors and dielectrics. And here the idea is simply that if you put a non-conductor and a dielectric in between a capacitor, it changes the capacitance. So put something in between there with a dielectric constant kappa, and then C goes to, C goes to kappa times C. So if you're doing a problem with that situation, then you just multiply the capacitance times kappa. And practically that's important because the way to make a capacitor is to have two conducting sheets, put a dielectric between them and roll them up, right? Make it compact. I discussed that the other day. Okay, good. That covers our chapter on capacitance, and we're next going to go into currents and some direct current circuitry. Let's set this up here. So electric current. Our next topic is electric current. Next topic, next chapter. Okay, next chapter, electric current. So what we're now looking at is electric charge that's moving. And for example, we could have a bunch of electrons moving. We could have positive charge, we could have a bunch of protons moving. But we're going to abstract away from all of that and just say we have a certain amount of charge passing. So I'm just going to put some dots here. These are charges, and I'll put some little speed indicators. They're moving here to the right, and they're passing through some cross-sectional area. Okay. So what we call the current is the amount of charge that passes through this cross-sectional area. It could be the cross-section of a wire or just a vacuum tube. The charge that passes per unit time, so we're going to define current I equals certain amount of charge passing through that cross-sectional area per unit time. Under circumstances, it can also be a vector. Right now, we're just looking at the magnitude. And the units are coulomb, I'll write it out, per second. So those are the units of current, and that is the ampere, just the letter A. So unit of current is the ampere. It's a coulomb per second. So if you're talking about elementary charges, of course, that's quite a few charges per second. And so even though we think of these, on the one hand, as little individual charges, on the other hand, if there's 10 to the 15 of them passing past some point every second, then we can think of it as just a fluid that's flowing. So that's why we have that word current. Okay. So the idea of something flowing. Good, so that's the first part of our definition. So I did mention a vector, and this is important for formal reasons. The direction of the current is the direction of positive charge flowing, okay? So the positive direction is, best way to formulate that, yeah, just flow of positive charges. So what if you have negative charges flowing, which is so often the case? Doesn't matter. So if you have, okay, here's the direction of current, then formally we're just going to call it that, and if we need it, then we'll know that the electrons are actually going in the opposite direction. But as far as our formalism goes, it's just the flow of positive charges. So a current here, like I've indicated, flowing from left to right. You don't have to worry about what the electrons are doing typically. The formalisms will just be built on the fact that it's a flow of positive charge. And so for example, if we have a battery where I've shown plus and minus like this, and we eventually have some circuit elements up here, then the flow is always going to be away from plus and towards minus, regardless of what those charge carriers are. Good. Okay, I have a little section here on the drift velocity or the drift speed. Yeah, that's actually worth talking about. So drift velocity. So the velocity with which the charges move can take on a huge range of values. So it's actually worthwhile to kind of define this. So what we're going to do is imagine we have a wire here, okay, and there's a segment in here, right, which will give the length of delta x. Kind of count what's going on in here. So I can, what I'll do is just write my delta Q over delta T, and then to kind of give us the N Q A V drift, okay, drift velocity V sub D. Cross-sectional area A. So those aren't the amperes right there. Cross-sectional area A. So what is this? We'll check it out on dimensional grounds. So what do we have here? Here's a number of charge carriers. Carriers per volume. So that's a number density, and then that's the charge, and then that's a cross-sectional area, and that's a drift velocity or drift speed. So you can check your dimensions. You've got number per volume, so you've got charge per volume times area, okay, that's charge per length times length over time. Okay, so that cancels the length and it turns into charge per time, which is what we had here, okay? But this expression is good to analyze for a couple of cases. What you'll find, and I think we have a good example in the book that I'll leave you to look at. For say a wire with some, say 1 ampere or something, the drift speed will actually be very, very slow. So you know, on the order of millimeters per second or even less. Okay. And that's if you have current in a wire. So let me just go ahead and give examples here. First one, current in a wire. See if I have some numbers here for you. I don't have the numbers here. You guys supply them. I just have that it's on the order of, V drift on the order of 10 to the minus 3 meters per second. It could be very small. On the other hand, you could dispense with this formalism and just go back to here and have charges zipping through a vacuum. Then your speed was not a drift speed at all. Then your speed is the speed to which those charges are accelerated. Under circumstances, that can be all the way up to the speed of light. So it's a huge difference here. So in vacuum, we're not talking about drift speed. Particles can have any speed as long as it's less than the speed of light. Speed of light, which we'll talk about later this semester, which is 3 times 10 to the 8 meters per second. So this second case here is not the drift speed. Very different. Here with the current in the wire, which is what we're going to be focusing on next, you're actually talking about constant speeds, this drift speed here, and that comes about because there's friction, there are collisions and things. which we'll get to. So it's just to note that this is not the drift speed, okay? Not drift speed. Huge range of different speeds possible. Good, and because I have an interesting problem that I'm going to assign, really based on this definition, where they have charged protons moving very close to the speed of light, and then you're supposed to figure out how many there are per volume, okay? So then you're just going to go straight back to this definition and figure it out, okay? You won't have to use this drift speed definition. Okay, so from here, we're going to go to Ohm's law. And then we'll actually bring in our circuit element. And in fact, we'll just do Ohm's law in a linear conductor. Ohm's law. This time we're looking at a wire again, and there's our long thin wire. There are charge carriers. They tend to be electrons, but there's going to be our direction of current. And there's a potential difference across the ends here. So you can imagine that we had hooked this up to a battery. And these are, of course, wires as well, but we're going to see away from that for the moment and think that everything's happening without friction here, but in this circuit element, there's some kind of friction due to collisions. And when I say friction, it's something, so here's a V, a voltage. There's something going on in here that keeps those particles from accelerating because they have this constant drift speed. Now, we know that if it were just Coulomb's law and you have charges, for example, going across a vacuum, they're accelerated. But if we have a constant speed for the current, that means there must be some kind of friction, and that's actually referred to as resistance. Okay. So I'm just going to put down the resistance. Let's see. I'm going to construct the resistance first. Now let's just go ahead and put this down here. Resistance. It's a kind of friction. And if we have a constant V drift here, and yet there's an electric field across there must be this kind of resistance. Otherwise, there would be an accelerated instead of a constant speed. Okay. So that's our explanation. And we're going to have Ohm's law V equals R times I. And this resistance here is built up out of a resistivity, and we'll talk about the units in a moment, times the length. So I need a length of this wire divided by the cross-sectional area. Cross-sectional area A. Which makes sense. This is a material property, and you can see that the longer the wire is, it scales in terms of the length and goes as the inverse in terms of the cross-sectional area here. So that's the resistance formula. the units in terms of Ohm's law right here are just volt per ampere. That's the ohm, and the symbol for it is the uppercase Greek letter omega. So let's go ahead and put that in a circuit element right away, and we'll actually have our first functioning circuit here. Okay, so this is constructing, you can say, calculating the resistance based on resistivity. Maybe I should put that down here. Rho is the resistivity. And by the way, sigma equals 1 over rho is called the conductivity. Okay. But yeah, let's get a circuit element here. And what I'll do is I'll draw a little picture, and then I'll do the circuit element right next to it. So we could, for example, have a car battery. They're labeled with a plus and minus, and we could be sending that to an incandescent bulb, which has a little filament inside. And since we have a plus terminal here, we could even say delta V equals 12 volts. Our battery, light bulb, direction of current. And the filament is so thin that it has a very high resistance, and we'll get to power in a moment, and it gives off light. Okay, it gets red hot, gives off light, but primarily in our discussion here, it gives off heat. In terms of the circuit elements, the same thing here would be this battery with delta V. In my case there, I just called it 12 volts. There's the plus, there's the minus side. And our resistor is just this line there giving a certain number of ohms. Okay, so that's our circuit element. There's our circuit, there's the direction of the current. And so far, we just know that we've got this delta V is R times I. Like I said, I can use these V's and delta V's pretty much interchangeably. And so yeah, not much more to say here until we've learned about power, expression for power. So that's what I want to get to. Let me consult my... Good. So let's see, let's label this. This is the first simple circuit. So, circuit with a battery and a resistor. Resistor. So yeah, there's the labeling. Delta V is so and so many volts. You got a current flowing from plus to minus. You've got the resistance R. And the example of that light bulb is a good one because we know these light bulbs give off heat. It's an incandescent bulb. Put that as a note here. Incandescent light bulb. Less common than they used to be, but this is for practical purposes very important. What's really being given off there is heat. So we want to go up to that energy and power discussion before we do anything else. Yeah. actually done very quickly. Back in the chapter on potential, we had an expression for energy, and we're just going to divide that by time and we'll have power. So let's call this little section electrical energy and power. Yeah, that's what I'm calling it. So next, electrical energy and power. So what was our expression for the electrical energy? Remember we had the work was equal to Q times V. I'm going to write Q delta V right now. I'm going to use the delta V in the situations where I'm actually putting some numbers in, because then I can say, for example, delta V equals 12 volts like I did right there, instead of V equals 12V, which is a little awkward. And it's a good nomenclature as well, because we're talking about a voltage drop. Be that as it may. So this was the energy stored when you had charge and a potential difference. Okay. So energy and what about power? Well, power we know is work over time. Okay. So if I just divide this by time, I'm going to have Q over T, which is charge per time, which is current. Okay. So what I'm going to have is power equals Q over T delta V, or current times delta V. This is very easy to remember. I delta V, because these are your watts, these are your amperes or amps, and these are your volts. So you'll never forget this. Watts equals amps times volts. And now we can go ahead and analyze a circuit like this completely. Okay. Once we have this power formula, and this actually has a lot of practical day-to-day use in your household. In your household scenarios, you often hook up devices with a certain power rating. You have a certain voltage rating. You have certain currents involved. I should point out, right now this is all direct current. The household wiring is alternating current, but we're going to inherit these same formulas with a little twist to them. So don't worry about that. We can use these for the general household situation as well. Okay, so there's our power formula, just current times voltage. And let me give some examples. Battery, so direct current. Which is all that we're doing right now. We have batteries with, in fact, you may want to look at your devices and see what you have in your day-to-day life. We have 1.5 volts, very current, very common, little AA, AAA, C, D cells, that kind of thing. We also have 9-volt batteries, and then 12-volt, those are our car batteries. These would be your AAA, AA, C, D cells. Okay. And these here, what do we call these? The kind you put in your smoke alarms and stuff. Okay, the little 2 terminals on top. Yeah. So consult the time once again. Okay, yeah, let's analyze that circuit up there with what we have here. redraw this over on the left side of the board. But I won't redraw the light bulb, that's what we just had here, but yeah, now we're looking at a battery, delta V, a resistor, R, we're going to have a current I like that. And think of the light bulb. So we have Ohm's law, and then we have power equals I delta V. We already see immediately that we could put the delta V in here from Ohm's law, and we would have I times R times I, so R times I squared. And they're equivalent, but they're actually often used in slightly different situations. So you gotta be careful. But here we go. So for our example, let's start with the car battery. So delta V is going to be 12 volts. And the power, at least in old incandescent headlights, we're just going to say is 60 watts. 60 watts. So what's the current going to be? Current. So we don't know the resistance yet. So we're going to use this one here. Current's going to be power over delta V. Going to be 60 watts over 12 volts. Going to be 5 amperes. Okay. What's the resistance? Okay. Now we've found the current. We can get the resistance is going to be the voltage divided by the current. So we have our 12 volt battery divided by 5 amperes, so that's just over 2, so 2.4 ohms. So those are pretty typical values. One important point that I should mention right now, there's a strong temperature dependence in resistance. So if you took this light bulb, hooked it up to an ohm meter, and measured its resistance, it would not be the same value that Ohm's law gives you, because this thing is running extremely hot. Okay, that's the kind of thing you run into when you're doing labs with these circuit elements. Let's see. Okay, one more. Let's see. Yeah, I'll put that as a note just so we don't. This value that I got is the one that actually is obtained from Ohm's law, and while the current's flowing through it while it's very hot. So this value for high temperature. High temperatures, exclamation. You actually measure the resistance of a light bulb, it's going to be completely different because it's running so hot in this case. Okay, good. But nonetheless, this is the actual resistance while it's running. Not every circuit element gets that hot. Okay. Okay, so I want to do one more thing before we do the direct current circuits, and that is to talk about batteries and internal resistance. So here I have Ohm's law, here I have a battery hooked up to a light bulb, and you could look at this thing and say, well, the current, did I solve it here? No. The current is the volts divided by the resistance. So as the resistance gets smaller and smaller, the current goes to infinity. And yet, if this is some little 1.5 volt AAA battery, it's hard to imagine the current going to infinity. So yeah, there's something in here that has not yet been elucidated. That's just a bit of an idealization. So that'll be our next and last topic for the hour. We'll just write down Ohm's law again. We're referring to that picture up there. What should we call this? Well, this is batteries and internal resistance. So the very simple case here, redrawing this, delta V, there's our circuit, and I'll just say this, from delta V is equal to Ri, I is equal to delta V over R, goes to infinity as R goes to 0. Question mark, okay, this is not true. It does not, in reality, it does not go to infinity, but, given this law here, it would. So what's going on? What should I have? This formulation. Can a battery deliver infinite current? The answer is no. And the reason is to properly describe this battery, we have to take into account its own internal resistance. So here's a battery. Here's what we'll do. So here's our delta V, but our battery has what's called an internal resistance built in. And then I'll draw this picture. So enclosed, right? You can't, in other words, you can't have this, in fact, we're already going to give it a new name. It gets the, uppercase epsilon, it's called the electromotive force. We'll see why later. But yeah. And the delta V is actually what we measure across the end of the battery. Okay. So this is an internal resistance. And the delta V is measured across the ends here. And no matter what we hook this thing up to, okay, so now we hook it up to a resistor. No matter how small this resistance is, this one is always there. This one cannot be changed. Okay. So the battery has an internal resistance, but we can do the same. We can do the same analysis that we did up there with this battery. Now Yep, now we have 2 resistors instead of 1. So Ohm's law still holds, but this internal resistance cannot be changed. So now what do we have? We have E minus IR. And if we complete the circuit, right, we've got the direction flowing this way. Complete the circuit, we have minus I lowercase r is equal to 0. Okay. So E minus I r plus r equal to 0. This is basically Ohm's law. You can see it right here. You have these 2 resistances, and this is in place of the delta V. So we have that. What about the delta V now? What is the, because that would be the actual reading across this battery. Actually, I'll just answer my own question. And delta V equals E minus IR. So this is the rating of your battery. These are your 1.5 volts on that D cell. As you hook it up and actually run something, then the voltage actually drops. And what you'll find is if you have too much load across the battery, and the lights, instead of glowing bright, will be dimmer. So yeah, we have that. And then there's also going to be a power associated with this. Let me just finish this. Is the voltage across the battery. So you can see there's its maximum rate. It's the rating of it. That's the maximum possible voltage. As you draw current from it, the voltage goes down across the ends of the battery. Should we do the power there as well? And of course from here, current, again, this labeled rating divided by R plus lowercase r. No matter how small you make this one's always there. Okay. So in fact, that would be your maximum possible current would be this voltage divided by that internal resistance. So that answers our question. My maximum that a battery can deliver is E divided by R, with that being the internal resistance. I think we'll leave it at that. So let's write down a homework assignment. I actually had, from the Capacitance chapter, a couple I wanted you guys to do. So this is homework 16. And what are these 2 chapters? 24 and 25. So the capacitance problems, and then the current problems, let's see, 29, 31, 32. I think they're actually kind of interesting. And for the current, I only had one here. Let's see if I can't find another for you. Yeah, 35 is a proton beam. Actually, let's do 37 as well. These are prior to these circuit element problems. I'm not sure. I think we'll do those next time. Yeah, we'll do those next time. Actually, this chapter has a lot of important and interesting stuff. So these were really just the fundamentals. Primarily, I wanted to get Ohm's law into play, but these do not yet involve Ohm's law. Be that as it may, see you guys next time.